not that far from today, so just keep it on your radar. Today's the 14th. Oh, happy Valentine's Day. The 14th, so we have the 16th, the 21st, and then it looks like, is the 23rd? Yeah, the 23rd is an exam. That's right before, is that Mardi Gras? Right before Mardi Gras? How long do we get off for Mardi Gras? We get 3 days? Just the Monday? We get all three of those off. So yeah, this is Mardi Gras break. But we'll have an exam just before then. It'll cover the fluids, body, the fluids, and probably the work, and all the work and energy, and maybe even a little bit more. But we'll just sort of see how far we get. Any questions or concerns or whatever? No? All right, let's sort of recap what we've been doing. Hey, Lydia. Been talking about work and energy. So remember, work is a force and a displacement in the same direction. And we can have forces that don't do any work, like I'm exerting a force, but since I'm not moving the thing, I'm not doing any work with that force. So you can have forces that don't do work. You can also have forces that do negative work. So like, for example, if I push this, there's a force that's doing negative work. What is that force called? It's called friction. And forces that do negative work take away energy. That's where the negative comes from. It denotes that we're taking away energy from the object. We talked about the work energy theorem, which is closely related to that, that if I give work to an object, I increase its energy. If I take work away, if I do negative work, I take away energy from that object. And then we have different types of energy. We talked about kinetic energy, which is the energy of motion. That kinetic energy, that's 1/2 mv squared. You're not going to have to calculate the kinetic energy, but you do need to know how it relates to both the mass and the speed. So like, for example, if I double the mass, I double the kinetic energy of the object. But if I double the speed, I quadruple the kinetic energy because you have that square relationship, that quadratic relationship, so where v is squared. And then we also talked about potential energy. Lots of different types of potential energy, but mainly we'll work with, gravitational potential. That is, if I move something within the Earth's gravitational field, I'm applying a force over a distance. So I give it a certain amount of energy when I get up to this point, and when I let it go, that potential energy, that potential for motion, is converted into kinetic energy. So anytime I talk about potential energy, I'm sort of talking about its potential to become kinetic energy, or potential to do work. All right. That was our expression for. Hey, Raj, that's okay. Our potential energy is mgh, and h refers just to the distance from some reference point. So, for example, if I have an object that has a certain mass, the distance h is just the distance it is from the ground. And when you drop the object, the potential energy is converted to kinetic energy. So just like I said there, that if I have an object with gravitational potential energy and I release it, then all that potential energy is converted now to kinetic energy as it falls towards the ground. All right, let's do a couple of these little quicker questions. We'll do the one on the left here. By what factor does the kinetic energy of a car change when you increase its speed by a factor of 3? You play softball too, Daisy? Yeah. It should be AA. Oh. I think you hold the power button down. Like if you hold the power button, yeah, and then you just type AA. Alrighty? I think the instructions are on the back, but you have that little cover on it. What happens if you triple the speed? What happens to the kinetic energy of an object? We're not doing real great on this question right now, so think about what is the expression for the kinetic energy And if you increase the speed by a factor of 3, how does that affect the kinetic energy? How is the kinetic energy related to the speed? Feel free to ask your neighbor. Yeah, we're sort of like every answer has an equal number of options right now. So if you ask somebody, you may or may not get the right answer. I'm going to write our expression for kinetic energy up here, and then I'm going to stop here in just a few seconds. Our kinetic energy is 1/2 mv squared. I'm going to stop at 148. 148. Okay, that's better than y'all were doing. The answer is C, 9. That if I triple my speed, then my kinetic energy is increased by a factor of 9. So actually, if I were to plot kinetic energy and speed, it looks like this. That as the speed increases, I need a greater increase. I need a larger amount of kinetic energy as my speed increases. Let's try this next one. That little function that I drew, that's a quadratic function. That's the k versus v squared function, if you remember from algebra or whatever you saw that in. All right, we'll stop at 115. 115. Is that all we have in here today? Yeah. All right, 115. 0 to 30. I can't even mark the right answer. Oh, wait, here we go. You're all wrong. Even after, yes. Even after I drew this graph over here. I thought, gosh, I'm not going to draw this graph because that'll just give away the answer. Look, let's look at this graph. This is actually kind of important. As I go from 0 to 30, as I go from here to here, that's 0 up to 30, the amount of energy that I require is this amount. That's the energy that I require. But watch, when I go from 30 to 60 miles an hour, this is the amount of energy that I require. I require a heck of a lot more energy. And the reason is that because my energy is proportional to V squared. So as V increases, the energy increases by a lot more because it's squared here. It's a quadratic relationship. This is why, in fact, and you can tell your friends this as they're speeding down the road, that your car gets worse gas mileage at higher speeds. You've heard this, right? Actually, with your car, there's an optimal speed that gets the best gas mileage. I don't know, it's like it used to be like 40 miles an hour. I don't think it's that anymore. My dad, by the way, drove 35 miles an hour everywhere, like even on the interstate. I drove to Atlanta with him one time, 35 miles an hour on the interstate. I thought we were gonna die. But the reason is because he knew that he got better gas mileage at that speed. Because the faster you go, the faster and faster you go, the more energy it requires. So the faster you drive your car, the more and more energy. And it increases quadratically like this. It increases a lot as you go along. So next time you're out with your friends and they're driving too fast, you can tell them, hey, did you know that the energy is proportional to the v squared? And so the faster you go, increasingly more and more gas you're going to use up. Okay, y'all got that? You'll tell your friends? Yeah, but I know that all of your friends are responsible people that drive within the speed limit. All right. So the answer there is B, because our kinetic energy is proportional to V squared, and so it requires a lot more energy to go from 30 to 60 than it does to go from 0 to 30. You with me on this? Yeah? You see now? If I were to ask you the question again, would you get the right answer, like right now? Yeah, I'm not going to ask you right now. All right, but I'll probably ask you on the test coming up. Oh, and by the way, a quiz Thursday this week. Yeah. Huh? The whole chapter. Yes. All right. So there are other types of energy. Mechanical energy is the sum of our gravitational potential and our kinetic energy. So our mechanical energy is U plus K. Is that what I meant? Yeah, is U plus K, and this considers energy from our position and motion. Your book describes this mechanical energy. Not all books will actually separate mechanical energy out, but position relates to what? K or U? Which of those energies is related to position? K or U? U, right. And motion is K, right. So if you want to, just to remind you, this is U, this is K. We have a principle, which is called or law rather, called the law of conservation of energy, or conservation of mechanical energy, sorry, what your book calls it. And that says that energy transforms from U to K or vice versa. It transforms back and forth, but the total amount of energy remains the same. All right, we'll work a problem, but first I want to show you a video. This is a video from the PBS series about the circus. PBS did this reality show about the circus. Are you all familiar with this? I think it's called Circus. And then they did some extra little episodes about the physics of the circus. And so this is just a video about the physics of the circus and conservation or transfer of energy. Let's see. 5, I think. Yeah, there it is. All right, so in that, Anna, this acrobat, she converted her energy from potential energy at the bottom, but it wasn't gravitational potential, it was elastic potential, right? Like the rubber band stretched out. Converted all that to kinetic, and then as she went up in the air, it converted back to another type of potential energy, which is gravitational potential energy. So that's an application of this conservation of energy. Let's imagine that we have a roller coaster. And here, at the beginning of the roller coaster, I have v equals 0. This is point A. And then it travels down, and then comes back up, and then it goes there. So which point, A, B, C, or D, is the kinetic energy of this object the greatest? At which point does it have the greatest kinetic energy? A, B, C, D, or are they all the same? So you can choose A, B, C, D, or E, all the same. And we'll use those options for the next two questions as well. Where is the kinetic energy the greatest? All right, we'll stop at 50. Say. Okay, good. B is right. The kinetic energy is greatest at the bottom. Now we'll come back and talk about that. But where is the potential energy the greatest? Is it A, B, C, D, or E all the same? Where is the potential energy U the greatest? Feel free to ask your neighbor. Okay, y'all doing really well. I'm going to stop at 30, at 40. 40. Okay, awesome. We'll come back to that. And now, where are U and K equal? That is, where are the gravitational and the potential energy equal to one another? At A, B, C, D, or is it all the same? Or pick your best answer. Pick the closest answer you can find. Where are the gravitational and potential energies the same? Oh man, y'all are doing great. Y'all rocking this. Okay, just a couple more seconds. Let's stop at 45, 45. Okay, good. C is right. So let me recap that. And what type of snacks do computers eat? Oh, y'all have heard that before? You see, don't. Who gave away my punchline? Alex, was that you? Microchips, yeah. What? Are you serious? She got my jokes. I'll tell you, like, I sent her my jokes and said, here, use these. But every once in a while, we get a student like Daisy who's in both classes. I have a student in my other physics class that's in both. I'm sorry, Daisy. You're not getting the full. You should ask for a refund or a partial refund anyway. All right. So where is K the greatest? K is the greatest at part B, because if we think about this in terms of like a bar graph, let's let blue be the kinetic energy. Up here, it has no kinetic energy, but it has lots of potential energy. Down here, it has lots of kinetic energy, but it has no potential energy because all that potential energy has been converted into kinetic energy. Here at point C, which you guys got correctly, where U and K are equal, this is U is greatest at A. At point C, it has half kinetic and it has half potential. And then down here at part D, what was kinetic? Was kinetic blue or red? This is U, this is K. Yeah, so blue down here, the kinetic energy is big and it has some potential, but not as much. All right, so we have this sort of trade-off between the kinetic and the potential. No kinetic, lots of potential. No potential, lots of kinetic. Equal of both, and then a little less kinetic, or a little less potential, a lot more kinetic, because it's at a lower height, and so it's going to be traveling faster. Well, y'all been on a roller coaster before? You travel fastest when you go down to the lowest points. Right? And then they use those chains to pull you up to the highest point. You're gaining all that gravitational potential energy, and then they just let you go. And all that gravitational potential energy converts into kinetic energy until you lose it because friction acts on the car and slows it down, and then they have to pull you back up to the thing. Did I tell you I went to Six Flags last summer? My kids, it was their first time ever to go to an amusement park. And my wife, really big into roller coasters. Like she grew up with roller coasters. She just loves roller coasters. I give or take them, but she loves roller coasters. That was like her big thing. Like I want to take my children on a roller coaster. And so we weren't sure if they were gonna like it or not. But we said as soon as we get in the door, we're just gonna shoot to the back and go to the Screaming Eagle at Six Flags, which is sort of like their mid-level roller coaster. Not the baby one, but not the upside down one either. And so we did, and the kids, they were all pumped. They were all excited. Yeah, let's ride this roller coaster. We were the only ones on it, so they set us right up front. And we got on there, and they let the bars down, and we started going out. And my son said, "No, I don't want to go." But of course, we were already going, and we went through, and he was like, "No, no, no." My wife had a great time, but they hated it. And so then we didn't get to go on another roller coaster until the very end. We sort of fooled them. We tricked them. We said, oh, they have this train that we're going to ride on. So we got to go on another one, but it was much tamer. she rode the Screaming Eagle, and then the miners thing, that train at the end. We offered that she could go by herself, but you know, it's not as much fun by yourself. All right, let's look at electrical energy. We have lots of different types of energy, and your book has, you know, paragraphs about each of these types of energy. We're going to see these because we'll have a whole section on electricity later, and we'll talk about, you know, electrical charges and the neurons, and we'll have a whole chapter on electricity as well as on light and heat and what have you. But we're just going to sort of introduce these different types of energy. Electrical energy is the energy of charges. Energy is greatest when charges are closer, because the forces are greater. You probably know the basics of charges, that if I have two positive charges, for example, that are really close together, they have forces that push them apart, right? Like charges will repel one another, opposite charges will attract. And if I move them really close together, the forces get really big. Whereas if they're farther apart, two positive charges that are farther apart, they have smaller forces that are acting on them. And so when I have them really close together, they have great potential for motion because the forces acting on them are big. If I let them go, they zoom apart. Um, Whereas if I have them kind of far apart, they have less potential for motion because their forces aren't as big on those. Let's have internal energy. You might call this chemical energy, although we'll see chemical again. But if I imagine that I have a bunch of particles that are moving around in a container, these are vectors. It's not like, what is that, the female or male sign? I don't know. Anyway, I have these gas particles in a container and they're moving around. Each of those particles has kinetic and potential energy. And so I can describe the internal energy of that system just based on the kinetic and potential energy. Heat is the transfer of energy from a hot to a cold object. That's the first law of thermodynamics. When heat is added, the temperature increases or it changes phase. And we'll see more on that later. We'll get into phase changes. And then later in this chapter. Chemical energy, we'll see this more a little bit later when we talk about food, but it's the stored energy in molecules and atoms. Right, when you eat something, those food items have actually chemical energy in them. Your body breaks down the atoms or molecules, and that creates energy in your body. We'll see that a little bit later as we talk about, you know, DMR and all that business. Electromagnetic energy, light radiation, I have a chapter on that. Acoustic energy, sound. We have a chapter on that. That's a fun chapter because we'll do a lot of sound stuff. And then nuclear energy we'll see again later in the semester. All right, so just to be familiar with those different types of energy, your book sort of discusses them in brief, but we'll see them in more detail later. Okay, so conservation of energy. We've already seen that sort of with the roller coaster, that as we have this transfer of energy back and forth, and for some reason your book divides up conservation of mechanical energy and conservation of energy. I think because we're going to get into the body and we'll talk about, you know, the body as a closed system. So whatever energy you put in, you know, is used in some way. An open system versus a closed system. That's all right, Kai. An open system says that energy or work can be transferred into the system. I like to think of this as like a box that's open on the top, and you can put stuff into the box, or you can actually take stuff out of the box. Right? You can put stuff in or take stuff out, an open system. Whereas a closed system, no work, no energy rather, or work enters or leaves the system. And so, you know, this is a box that has the lid closed. And so nothing's going to get into that thing. It's just going to sort of bounce off. So we'll typically talk of our systems as closed systems. You can think of your system in a couple different ways. Like if you have you can make your system bigger and bigger. So like if you have a guy on a bicycle that's riding a bicycle, then you could sort of think of that as a closed system, except you have to put energy into the guy in order to make the bicycle work, right? Because he has to eat or whatever. But as you make your system bigger and bigger and bigger, then eventually you'll get to a closed system. So the universe, for example, we think of as a closed system, that there's no energy coming into the universe, no energy going out of the universe. So in a closed system, the total energy remains the same for all time. System is not closed. We can enlarge the system. I said that. So a moving bicycle is not a closed system. Kinetic energy appears and, sorry, let me find out where I am here, and causes the appears and causes the bike to move. However, if you include the man on the seat, it is closed. Right, so if we just think of the bicycle all by itself without the guy, that's not a closed system because we have energy somehow coming into the bike and making it move forward. Uh, However, if we consider that there's a guy on the seat that's actually pedaling it, right? If we imagine that we have, you get the idea, the bicycle here, that's a guy on the bicycle. If we take the system to be this entire thing, then that is a closed system, or we can think of it as a closed system. Um, the energy is converted from the man's muscles, which gain energy from the food we eat. And as I said, the universe we think of as a closed system. There is no energy going into or out of that system. We'll think of the body as a closed system, that the energy that goes into the body, uh, that once it gets into the body, it's used for some purpose. All right, we need to define power. Power is just the rate at which work is done. Power then is work over time, or sometimes you might see power as energy over time. The unit, remember the unit for energy is a joule, so the unit for power is 1 joule per second, and that is equal to 1 watt. So the energy, the unit for power is the watt. It was a scientist, James Watt, I think, back in the 1800s, who did work on this, developing electrical things. All right, we'll see power a little bit later. Okay, efficiency. This will become important again later, but let's just sort of define it now. This describes how much energy is converted in a particular task. You've probably defined efficiency before. You've probably seen this before, either maybe in some of your classes here or in high school. But efficiency is defined as the output power, P out, over P in, times 100% to make it into a percentage. This can also be given in terms of work. Actually, I'm getting these switched up. Where energy is work output over the energy input times 100%. So for example, if I put in, 100 joules of energy, but I only put out work of 20 joules of energy, then that would be 20 over 100 times 100. That would be 20% efficiency. Right? So something that is more efficient will use more of the energy that goes into the system. Where does the lost energy usually go? Does it usually go into heat, sound, gravitational potential energy, kinetic? If you have a machine or a body or whatever, where does most of the energy that's lost usually go? Because if we have something that's less than 100% efficient, that means that you're losing energy along the way. Where does that energy usually go? It usually goes into heat. In fact, we'll see later. I'll bring in the infrared camera when we get to this, but our human bodies actually put out a lot of heat, right? In fact, we put out about the same amount as a 100-watt light bulb, which can get pretty hot. You're like a bunch of 100-watt light bulbs sitting around. So most of the energy that we lose, so we say, goes into heat. Some of it goes into those other things, but most of it goes into heat. Let's try some of these calculations. This one on the left, rather. An engine has an efficiency of 20%. It produces an output work of 20 joules. Then how much energy was lost? I'm not asking how much energy you put in. I'm asking how much energy did you lose when this engine put output of 20 joules? Okay, many of you have the right answer, but about an equal number of you have one of the other answers that are wrong. Feel free to ask your neighbor what they put, or if you feel really confident, turn around and tell your neighbor what you put. All right, let's stop at 120. 120. Okay, good. B is right. You probably see one like this on the test. So let me show you. Our output work, let's go back up to this equation. On the test, there'll be simpler numbers like this, so you won't need a calculator or anything, but uh, so our output work is 20 joules. So I'm just putting it in here, 20 joules divided by my input. I don't know how much energy we put in, times 100. That's equal to, we're told, 20%. Times 100 is 20%. So if I'm getting 20% efficiency, if I get 20 joules out, that means that the energy that I'm inputting must be 100 joules, right? I put in 100, I get out 20, that's 20%. 20 out of 100 is 20%. So if I'm putting in 100 joules, then that means that I'm losing 80% of the energy that I'm putting in, or 80 joules. 100 minus 20 equals 80. Okay? Look back at the old test. You can see some other questions regarding that, but you'll probably have a question on efficiency. It'll probably look a lot like this, some different numbers, but a similar thing. Make sure that you're careful what I'm asking for. I'm asking for the lost energy or the total input energy, because here the total input would be 100, not 80. The total amount of energy that you put in would be 80. Or I could ask you, I could give you the total input energy and the efficiency of whatever device it is, and then you tell me what work is actually output or what energy is lost from that device. Let's see, we already answered this one. The answer was A for the lost energy mostly goes into heat. All right, let's so let's go to the back of the book. In the back of your workbook, you have some old exams. Let's just do a few questions. Just to practice this. Let's try number 24 here. I don't think you have page numbers back there, do you? Yeah, you just have the exam page numbers. It's on page 3 of probably exam 2. So let's try number 24. Is that exam 1? Seriously? Whoa. Okay, exam 2, page 3. Object is traveling at a speed v and has a kinetic energy k. If it speeds up to 2v, what is the object's kinetic energy? All right, let's stop at 103, 103. Just a few more seconds. Okay, remember, this is sort of like the 30 to 60, 0 to 30. My kinetic energy is 1/2 mv squared. And so if I double my speed, the kinetic energy quadruples because this 2 is squared, and 2 squared is equal to 4. So E is the right answer here. Um, let's try number 22 here. Number 22. If I do negative work on an object, what happens to the energy? Does it oscillate, remain the same, decrease, or increase? If I do negative work on an object. If you do 22, we're going to do 27 next. So 22 and then 27, but right now 22. All right, we'll stop at 56. I guess everybody. Oh no, 58 I'll go to. Okay, awesome. C is right. Uh, negative work means I'm decreasing the energy, right? Like friction does negative work. And now let's try 27. 40% efficient. I put in 100 joules of energy. How much will the system do? How much work does the system do? All right, I'm going to stop at 40. Stopping at 40. It's 5 more seconds. Guess if you're not sure. Okay, no, the answer is C here. Uh, I'm asking a slightly different question than what we were asking before. Before we were asking how much does it lose, and that's what you were thinking here. It's losing 60 joules. But if I have a 40% efficient system, then I put in 100 joules. That means I get out 40 joules. That it'll actually do 40 joules of work. So I could say my efficiency is 40%. That's equal to the work output over the energy input, 100 times 100. And so this work is equal to 40. If I have a 40% efficient engine, I put in 100 joules, I get out 40 joules. I lose 60 joules, but I get out 40 joules. All right? If you're having trouble with those, look back at some of the other old tests. There are other questions that are similar to this, but or you could come see me too. We can work on it together. I read I'm going to get the numbers wrong because I don't remember the numbers, but the point is that the human body, in comparison to, say, an internal combustion engine, is a lot more efficient at using its energy. And somebody asked, like, if you could express your body's efficiency in terms of, like, miles per gallon, because that's what miles per gallon, that's a measure of efficiency. How much do I get out the miles per what I put in the gallons of gas? So like if a human could drink a gallon of gas and convert that to energy, what if it, like how many miles per gallon would you get? What do you think it would be like? 30, 40, 50 miles a gallon? 60 miles a gallon? Like how far could you run on a gallon of gas? Huh? 30? It was like thousands of miles. Isn't that amazing? Because the human body is just so much more efficient. You think about a car, man. The engine gets immensely hot. You're making all sorts of noise. It just loses lots and lots of energy. But the body is actually very efficient at converting chemical energy, like in gasoline, into kinetic energy. Don't run and drink gasoline, okay? That's not good for you. But my uncle, can I tell you a little story? We're from Mississippi, right? And we used to run out of gas a lot. And my uncle had a bunch of cars. And so he would go out, and whenever he'd run out of gas in one car, he'd siphon gas out of the other cars. You ever siphon gas with a garden hose? You've done that? Okay, well, you take your garden hose, you stick it down, and first you blow into the garden hose to make sure there's gas in the tank. And then you like suck up a little bit so the gas comes up into the garden hose. But this is the tricky part. Because as the atmospheric pressure is pushing down inside the tank, pushing it up into the thing, you want to get the hose out of your mouth before the gas rushes into your mouth. Anyway, and then you put it over. But many times we've had a mouthful of gasoline as we siphon gas out of our vehicles into other vehicles. What? Yeah. All right. Let's go back to temperature and heat. We can come back and practice these later. So back to page 40, I think. Okay, you need to be familiar with three temperature scales. That is, you need to know what they're based on, and you just need to know what they're based on. And you need to sort of know some basic temperatures in those scales. The first is the Fahrenheit scale. Fahrenheit, by the way, Fahren is German to drive, and then height is like heat, so driving heat. Fahrenheit. Um, the Celsius scale, and then one that you might not have heard of is the Kelvin scale. I'm sure you've heard of Fahrenheit and Celsius. The Kelvin is actually the SI in the SI system of units. It is the SI unit for temperature. So often, like if you're using the ideal gas law, for example, you need to use your temperature in Kelvin. All right. Um, I'm sorry. Right. So Kelvin is based on absolute zero. We'll talk about that in a second. So for Fahrenheit, it's based on two temperatures. It says that the freezing point of water is 32 degrees. And it says the boiling point of water is 212 degrees. And so that's what we have over here. They say this temperature, 212 degrees, we will define as the boiling point of water. So the temperature at which water boils, we say is 212 degrees. And then we say the temperature at which water freezes is 32 degrees. We're taking that temperature at which water freezes and we're saying this is 32 degrees. This is what we're defining as 32 degrees. And then, you separate that into pieces. Once you get 2 points on a line, you can separate in between them. Between 32 and 212, you have what, 180? Is that right? 180 degrees? Yeah, 180 degrees. And so that's what sets the size of the scale in Fahrenheit. Celsius, in a very, very similar way, we say that the freezing point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. So this is 0, this is 100. Which is bigger? Is a Celsius degree bigger, or is a Fahrenheit degree bigger? That is, if I have a change in temperature of 1 degree, is 1 degree Celsius a bigger change in temperature, or is 1 degree Fahrenheit a bigger change in temperature? Think about how your scales are laid out. Right? I mean, I've drawn the, the degree marks for Fahrenheit. What about for Celsius? Which one is bigger? Which causes a bigger change in temperature? A change in 1 degree Celsius or 1 Fahrenheit? In temperature, like say it doesn't matter what the actual temperature is, but I'm just changing by 1 degree. I'm increasing my temperature by 1 degree. Which of those is a bigger increase? The Celsius or the Fahrenheit degree? A or B? All right, let's stop at 105. 105. was A? Celsius? Yeah, A is right. Notice that I have 180 degrees between here and here. Between 32 and 212 is 180 little increments. But between 0 and 100, I only have 100 increments. So this change in temperature is much bigger than this change in temperature. A change in 1 degree Celsius is much bigger, all right? I want you to just be familiar with some different temperatures. Well, first I want you to be familiar with that you can convert between Fahrenheit and Celsius. Uh, I give you these formulae. You're not going to actually need to use them, but the formulae are here. The Celsius temperature plus 32. So if I have a temperature in Celsius and I want that temperature in Fahrenheit, then I would just convert it in this way. Put in the Celsius temperature and get that in Fahrenheit. In a similar way, the Celsius is 5/9 times TF minus 32. All right, so if I wanted to convert 70 degrees Fahrenheit, what I would do is I would say 5/9 times 70 degrees Fahrenheit minus 32, and that's equal to approximately 21 degrees Celsius. And then similarly, if I wanted to convert 37 degrees Celsius, I would say 9/5 times 37 plus 32, and this is approximately 90. What do y'all know? What is that approximately equal to? You ever hear 37 degrees Celsius? It's your body temperature, right? So it's about 98 degrees. So those are just a couple temperatures that I want you to know. The room temperature in Fahrenheit, which is about 70 degrees, is 20 degrees Celsius, and your body temperature is about 37 degrees Celsius. Just two temperatures, just to sort of give you a reference point for those temperatures. All right, so no room temperature in Celsius is about 20 degrees Celsius, and your body temperature is about 37 degrees Celsius. Once again, another way that you can be cool to your friends. If you walk around and talk about the temperature not in Fahrenheit but in Celsius, and you say, gosh, it's such a nice day outside. It's like 20 degrees out there. Or you say, boy, it's so hot. It's like 37 degrees outside. All right, and then they'll begin to think that you're very interesting and enigmatic, or maybe they'll just think you're an idiot. I don't know. But anyway, I want you to know those Celsius temperatures just as a reference point. Okay, the third scale that I want you to know is the Kelvin scale. This is a little bit different. It's based on absolute zero. And a temperature we call the triple point of water. So if this is our thermometer, this is absolute zero. And then up here, we have the triple point of water. And we say this is 0 Kelvin. We say this is 273 Kelvin. And then we set the values in between. Absolute zero is the lowest temperature. It's a theoretical temperature. It's the temperature at which all motion ceases. So in your body, you have a certain temperature. But if you could get your body really cold to close to absolute zero, you would still have the electrons in your body moving around. I mean, you'd be long dead at this point. But your electrons would be moving around in your body. But if you could actually stop those electrons from moving, that's what we would call absolute zero. So absolute zero is a theoretical temperature at which all molecular motion stops, all atomic motion stops. It's very difficult to get down to that temperature We have a device in a couple rooms down the hall that gets down to a few millikelvin or maybe even nanokelvin, but you have to use liquid helium to get down to that temperature. So some instruments try to get down to those low temperatures because you get rid of the motion of the molecules. It gives you less infrared noise or vibrational noise. The triple point of water, you don't really need to know this, but the triple point of water is the point at which water exists in all three phases, as a liquid, as a gas, and as a solid. Actually, yeah, let's do know that. The triple point of water, water exists as a liquid, solid, as ice, as water, and as a vapor or as a gas. And it's a point that's very close to 0 degrees Celsius. It's just slightly above 0 degrees Celsius. The Kelvin degree is the same size as the Celsius degree. That's by design. All right. So what's bigger, the Kelvin or the Fahrenheit degree? The Kelvin is bigger. The Kelvin and the Celsius are exactly the same size. They're not the same temperature. So like 0 Celsius is freezing point, but 0 Kelvin is like hella cold, right? It's absolute zero. And um, but they have the same size of degree. All right, let's look at heat. Heat is the transfer of thermal energy. The total amount of heat inside an object, or let's see, no, I'm sorry, not the total amount of heat. The total amount of energy inside an object depends on the type and amount of material. And this is called thermal energy. The thermal energy is also related to the temperature. If I have an object that has a higher temperature, then the materials inside it are going to move around more. So the hotter you get, the more your molecules vibrate and move around. And that's what actually gives us thermal energy. Thermal contact is referring to when two objects are able to transfer heat. Your book talked about this. So I can have thermal contact like with the board if I touch it, or I can also have thermal contact with the board if I take a conductor and put it up next to the board. You ever cook marshmallows over the fire? Yeah, we do too. And we used to have these little short roasting sticks that were made out of metal, and you hold them in the fire, but if you hold them in there for more than a few minutes, the heat travels up the thing, and then, you have to put it down because it gets too hot. But then we got these fancy, dandy marshmallow forks. They get really long, they extend out, and they have plastic handles. You know what I'm talking about? So that when you put them into the fire, you're not in thermal contact. You're actually protected because one, you have a longer distance, and then you also have the plastic handle to insulate it. So thermal contact just refers to being able to transfer heat. Thermal equilibrium, when there is no flow of heat between two objects. This only occurs when you have the same temperature. And then we'll talk about changing phase from solids, liquids to gases next time. Or not next time, later. Let me see, I brought some things I want to go ahead and show you since I have it here. We're going to get to this a little bit later, but it's sort of related here as well. I have these two blocks. They've been in my bag all morning. I want you to tell me which one is colder. So can you touch them? Which one's colder? She said this one. Just a few of them I might do it. Okay, so you touch it and tell me which one's colder? This one, she said. That was the same one that Taylor said. Robin, this one's colder. All right, Stefan, can you try to? All right, do y'all agree? You know, this one they say is colder. Listen, my daughter, she gets into her bed in the wintertime, and she always wants to um, not get under the blanket. She likes to sleep on top of the blanket, and she pulls a blanket on top of her. Why does she do that? Because you get into the bed, and what's wrong with the bed? The sheets are cold, right? And she complains, "Oh, Daddy, my sheets are cold." And I say, Ada, your sheets are exactly the same temperature as your blanket. Because you know what? The sheet and the blanket have been touching. They've been in thermal contact all day, and they're exactly the same temperature. They're exactly the same temperature because they've been sitting next to one another all day long. And now they're in thermal equilibrium, all right? So they have exactly the same temperature. And similarly here, these have the same temperature. Like this is a thermometer. You ever seen one of these? It's an infrared thermometer. It tells you the temperature, like that's 21.4 degrees. Hey, gosh, it's cold in here, right? So that's Celsius, right. So I'm going to measure the temperature. Here's this one that y'all said was hot. It's 21.4 degrees. And now this one is 21.3 degrees because y'all are touching it. All right. So, so these have been sitting in the bag together the entire time, exactly the same temperature. Okay. This is the one that felt warm, and this is the one that felt cold. But it's just like the sheets that they're exactly the same temperature. Now I want to show you, I'm going to put some ice on it, and I'll come out here. I might be able to see. If y'all want to get up on the edges and see, I'll put some ice on this. And which one do you think is going to melt faster, or will they melt the same? Will it be the quote hot one, the cold one, or will they both melt the same? Now we've already determined they have the same temperature, right? Which one do you think? Or will they both? This is ice. I'm gonna put ice on it. Will they melt the same, or will they be different? First, will they be the same or different? What do y'all think? They have the same temperature, right? Does anybody think different? They are different textures, yeah. All right. Well, this is the hot one, and then this is the cold one. But they're actually the same temperature. Right, so I'm gonna put them on there. Anything happening? Is it? No. All right. Let's put this one. This is the cold one. Can y'all see it? What's it doing? No, not because they were touching it. No. It is a different material. Right. Look, I mean, it's almost completely melted. No, no. That's a good question. All right, one, why did it feel different, first of all? And then why is it melting? And the answer to those two questions the answer is the same answer. Why is it why did it melt so much more quickly? You want to feel? It has to do with the material, right? And it's the same reason that my daughter complains about her sheets. It's colder now because I had the ice on it. All right, y'all ever heard of thermal conductivity? Okay, we're going to talk about it next time. But thermal conductivity describes how quickly something conducts thermal energy. Right. So this is plastic and this is aluminum. Which one conducts thermal energy more quickly? The aluminum does. What about in my daughter's bed? Which conducts thermal energy more quickly, the sheets or the fuzzy blanket? No, it's the what? The sheets, right. That's why they feel cold. Just like the aluminum, that it feels colder because it conducts heat away from your body. So when you touch it, it immediately sucks heat away from your body. And that's why it feels cold, because it's sucking heat out of your fingers. It's not about texture, it's about the material. Because this has electrons in it that can move around freely, that will transfer heat quickly, In this one, the electrons are all bound up and they can't move around very well. So it's not the texture, it's not the weight, it's the makeup of the material. All right? You want to pass these around? You can feel them if you like. All right, we'll get to thermal conductivity, but I had that ice and I wanted to show you. All right. Three phases of matter. I know this: solids, liquids, and gas. Hey, have y'all ever heard the "They Might Be Giants" song? Do y'all wish to hear it? Okay. It's kind of a kid's song, but I like it. I think it's a good song. But, but I don't smoke anymore because it's very bad for you, and you shouldn't either. All right. All right. So need to know sort of the basics of the different phases of matter. I'm not going to go over those, but you know, solids are solids, and liquids, they can flow around, and gases fill the size of their container. Solids, liquids, and gas. You can have phase changes between these, where you go from, you know, a solid to a liquid to a gas as you increase the temperature. The specific heat describes how much energy is required to change the temperature of an object. So some objects have a very high specific heat. They require a lot of energy to change the uh, the temperature of the object, and some objects have a low specific heat. They require a very small amount of energy to change the temperature of an object. You might have seen this equation before. I'll write it in just a second again. But Q equals mc delta T. This is our specific heat. This is the heat, and then this is the change in temperature, and this is the mass. We'll see that again later. But the specific heat says that if I have a big specific heat, then I need a lot of heat to change the temperature. Y'all done with those? Thanks, Raj. The latent heat is the amount of energy required to change phase. It describes how much energy to change phase is required to change phase. All right. And then calorimetry is the study of how these materials change phase. So for example, this describes sort of the different phases that you can go between, that you can go from a solid to a liquid through melting. You can go from a liquid to a gas through vaporization, or from a gas to a solid by deposition, it's called, where you actually, the solid will actually depose onto a surface. Or you can go from a solid to a gas, or a gas to a liquid, or vice versa by those different mechanisms. And then we're not going to talk about plasmas, but you can go from a plasma, from a gas to a plasma. A plasma is like the surface of the sun. A plasma is like those balls that they have, the glass balls with the bzzz, you know what I'm talking about, in Spencer's or wherever. Right. I know y'all don't go to places like that, but if you did, you would see those glass balls that have the bzzz things coming out. So, and you put your finger on it. That's a plasma. A plasma is just a gas that is completely ionized. The electrons and the protons are all separated. Okay. On the sun, that's because it's really hot. Right. The sun is a big ball of gas. It's really hot. On those little glass balls, it's because of the electrical energy that actually separates the uh, the electrons from the nuclei. So, if we think about this is the amount of energy that goes into a substance, and then this is the temperature. Like so, if I start with ice right here, as I put energy in, the temperature increases. And we can calculate the amount of energy. That's this Q equals mc delta T. But then at some point, I get ice, and has some water mixed in with it, but at some point I get up to 0 degrees Celsius, and I still have ice at 0 degrees Celsius at this point. I've raised it up to the melting point, but it has not yet melted. Then I have to put in the energy, which is due to the latent heat that's required to change this solid into a liquid. So there's this additional amount of energy required to go from being ice at 0 degrees to water at 0 degrees. So you put all this energy into it, and all it does, it doesn't change temperature, it just changes phase. Now this is important because later we'll talk about the body's primary cooling mechanism, which is what? Sweat, right? We get water on our skin, and when water is on our skin, it turns from a liquid to a gas, and that latent heat is what carries energy away from our body and allows us to cool a lot. It's actually a very effective way to cool our body. So this is our latent heat, and then we get water at 0 degrees Celsius, and as we increase the energy we add more energy in this direction, it raises the temperature. And then I get water at 100 degrees Celsius. It's at the boiling point, but it's still a liquid. But I have to put in all this energy, which is the latent heat of vaporization, we call it, to change the water to steam or to change the water to a vapor. So this latent heat, all this energy is the latent heat or the energy to go from a liquid to a gas or a vapor. And so, as I said, this comes up a lot as we talk about evaporation in sweating. But I just want to make the point here that this latent heat of vaporization, we call it, is really big. That steam has a lot of energy. It requires a lot of energy to go from a liquid to a gas. And that's why sweating is so effective, because when we have liquid water that becomes a vapor on our skin, it carries away that latent heat from our body. Just like the aluminum block took energy away from your fingers, and that's why it felt so cold. In a similar way, when the water on your skin goes away, it pulls that energy out of your body and causes you to cool. That's also why steam burns are so terrible, because they just have a lot of energy in them. Okay, let's try these couple clickers. I know y'all ready to get out. We'll be done in just a couple minutes, okay? The Fahrenheit scale is based on the freezing point and which of these other two temperatures? All right, we'll stop in a few seconds at 35, 35. Go on to the next one if you like. Okay, good. B. B is right. The boiling point of water. By the way, I read this article. This isn't a joke. I'll tell you a joke in just a second. I read this article, and they said that on multiple choice exams, that usually the longest answer is the correct answer. That they did this study and they found people that wrote their exams, the longest answer was the correct answer. But that's not true for me because I've been trying to watch that. But it was true that because, the people that wrote the exam, they wanted the correct answer to be perfectly correct. And then the other answers, they just didn't spend as much time on crafting the answer. So watch out, though, because not necessarily the case for me. I mean, this was not the longest answer. Yeah, it's the shortest answer, right? But B is the right answer. Oh, if you ever get cold in this room? You ever get cold in here? If you ever get cold, you have my permission. You just come and go to one of the corners of the room. Because over here in the corner, it's always nice and warm. It's like always 90 degrees over here. Have you heard that one, Daisy? Yeah. Let me get on to her. All right. Let's try this next one. Which of these changes in temperature is smaller, or do they all represent the same change in temperature? All right, I'm going to stop. A few seconds, 28, 29. Awesome. Okay, good. That's right, Fahrenheit, because between the boiling point and freezing point, I got 180 degrees. And so that's a much smaller change in temperature. We'll do these last two and then we'll wrap it up, okay? So what is the latent heat of fusion? Oh, I don't think I told you all this. Did I tell you the latent heat of fusion? Uh, I'm going to tell you the answer. It's solid to become a liquid, right? You have latent heat of vaporization, and then you also have latent heat of fusion, which for in this case is A, the energy required for a solid to become a liquid, or vice versa for a liquid to become a solid. I'm going to stop at, so A is the answer. Stop at 28. I'll do this last one. We still have like 30 seconds. Which contains more energy, water or steam at 100 degrees Celsius? Or do they both contain the same energy? We call that enthalpy. So your answer, you can go. All right. Quiz on Thursday. Reading quiz at the beginning of class. Y'all have a great day, okay? You want to know the answer? Okay, it's B is the right answer. Because you have that extra heat of vaporization.